Hello friends, welcome to VK Lectures. In this lecture we are discussing about the ensemble theory and thermodynamical potentials. The ensemble theory. The definition for the ensemble is it's a large number of non-interacting and independent systems. So it's any ensemble is a group of non-interacting and independent system. So it's a group of non-interacting and independent system. Now what happens? The member of the ensemble, that means any small entity in the ensemble of this group, or the member of the ensemble is called the element of the ensemble. Okay, so now about the member of the ensemble, that is element. The element may have same macro state, so macro state of the element can be same but different micro state. So this is the general idea of the ensemble, and there are different types of ensembles. Namely, we have a microcanonical ensemble, canonical, and grand canonical. Now, microcanonical ensemble is an isolated ensemble. Isolated, which means there is no exchange of particle. No exchange of particle. That means from one ensemble to another there is no exchange of particle, which means dn is equal to 0, and it is defined in terms of energy, the number of particles, and the volume. Now coming to the before that, it's isolated, no exchange of particle, and as well as no exchange of energy. Okay, it's a completely closed system. Now not the term closed cannot be used, the term has to be used is isolated. Now coming to the canonical ensemble, it's a closed system. So canonical is closed. Now here no exchange of energy, not exchange of energy, no exchange of particles, no exchange of particle, there is no restriction on energy can be transferred. Okay, so but there is no exchange of particle, and the macro state is given in terms of the temperature, the number of particle, and the volume. Now coming to the grand canonical, it is also called open system, where there is no restriction on energy or the number of particles. Both energy and number of particle can be exchanged. Energy and number of particles can be exchanged between the macro states. Okay, so each macro state is defined by temperature, volume, and the chemical potential mu. Now let us discuss about the canonical ensemble. The ensemble where the number of particle remains constant, number of particle remains constant, that means there is no exchange of particle. So there is no exchange of particle here, so that is right, no exchange of particle. This is number, which means dn by dt is equal to 0, which means n is constant. But similarly there is another parameter, which is the energy get exchanged, energy exchanges or energy exchange is possible. So in such situation we can write dE by dt is not equal to 0, which means dE is not constant. So if E is not constant, we have to find the average value of E, which is given by sum over S, ES representing the one of the state energy, and PS represent the probability of this state. For example, here we have 4 states given like this. This is E1, E2, E3, E4, and the probability of finding the particle in first state is P1, P2, P3 and P4. Then the expectation value of the energy E is sum over E1, sum over I represent the state, EI, PI, the same thing what we have written, and also this is equal to E1 P1 plus E2 P2 plus E3 P3 plus E4 P4. So this gives the average value of the energy. Okay. Now similarly we also have these sum, the probability, total probability equal to 1, and sum over PS, sum over S PS equal to 1. So these are the two ideas regarding the canonical ensemble. And now let us also bring a new term here, which is called the partition function. Partition function, and this partition function is given by Z is equal to sum over S e raised to minus beta ES. where beta is equal to 1 by kbt, and kb is a Boltzmann constant, and T is nothing but the temperature. So partition function is Z uh, given by E sum over S e raised to minus beta Es, and what is the probability? Probability of finding particle in S state. So that is given by in S state. Sum in general in S state is given by Ps equal to e to the power minus beta Es divided by the sum over S e to the power minus beta Es. So this for example, if you want for the finding the energy in the first state P1, that is equal to e to the power minus beta E1 with respect to this example, beta E1 divided by sum over S e to the power minus beta Es. Here you have to add all the probabilities. So total probability will be equal to 1. Now coming to the partition function. What does it tell you? Partition function is precisely it is sum of all possible microstates. Then what does it tell you? What does partition function gives? So it is similar to this wave function in quantum mechanics. Which means that through partition function z equal to sum over s e to the power minus beta es, through this function we can calculate other physical parameters or physical quantities, such as the average energy or energy, then after that energy we can also find the entropy, then Helmholtz free energy, etc. Now so here from this example of z equal to sum over s e raised to minus beta s, that is the partition function z, we know that any canonical ensemble can have the discrete energy level which corresponds to the quantum system, as well as the continuous energy level. which corresponds to the classical system. Okay. Now coming to the discrete energy level, we will have discrete energy level. So here in the discrete energy level, we should first be talking about non-degenerate energy level, non-degenerate energy levels. So what do you mean by non-degenerate? No two energy states, no two energy states has same energy, or energy levels has same energy. For example, here we have 1, 2, 3 and 4 energy levels. The first energy levels E1, second one E2, E3 and E4. So the partition function Z can be written as the sum over S e to the power minus beta Es. That is the partition function. Corresponding to that, we have the probability Ps given by e to the power minus beta Es divided by sum over S e to the power minus beta Es, and this is equal to e to the power minus beta Es divided by the denominator is nothing but the partition function Z. Now talking about the average energy, the average energy is given by E, that's equal to sum over Es Ps. Now this is also given by the letter U, indicating the average energy of the system. Now here this indicates sum over S, this is sum over S, Es. Now Ps is equal to, we already have the Ps value, Ps is equal to e to the power minus beta Es divided by Z, where Z is the partition function. So Es e to the power minus beta Es divided by Z, sum over S. So this is the equation for the average energy. Now this is the case for average energy in discrete energy levels. Now let us see for discrete and degenerate. So sorry, not degenerate. Now for a degenerate state, degenerate states. Now this means you have two energy levels with or two or more energy level with same energy value. So for example, let one energy level get split into two values, okay, and another second one split into three energy levels. Okay, so this one will have the same energy. This is E1, this is also E1, this is E2, E2 and E2. So here we have two energy levels with energy E1, and here we have three energy levels with energy E2. Now let this be equal to G1 or G2, or this is G2. The G represent the degeneracy. G is represent degeneracy. That means how many levels are there with the same energy, degeneracy. Now in that case, our the partition function z is given by sum over s, there's another term gs, e to the power minus beta es, just an addition of the term gs here. Similarly, the probability ps will also have the same term, gs e to the power minus beta es divided by z, and we have the average energy E given by sum over S Es e to the power minus Es, there's another term Gs, Es e to the power minus beta Es divided by Z. So this is the average energy. So here we have a question. Consider a system with energy levels minus E, 0 and E. Okay, so here also. Now find the partition function, the probability for each state, and the average energy of the system. So these are three energy levels, 1, 2 and 3, with the energy value minus E, 0 and E. Now here we can write the partition function, given by z is equal to sum over s e to the power minus beta es. So the first one will start with 1 e to the power minus beta es, that is minus e, plus e to the power minus beta into 0 plus e to the power minus beta into e. So it adds up to e to the power minus beta plus e, so that is e raised to minus beta e, plus e to the power beta times 0, that is 1, plus e to the power, this is minus beta e. So this is the partition function here, and now we need the so okay, once we have done the partition function, we can find the probability P1. Let us take P1. Before that, let us write the probability for PS. PS is equal to e to the power minus beta es divided by the partition function z. So with this we will find P1, we will keep the z as it is. So P1 is equal to e to the power minus beta, the first state has the energy minus E divided by Z. So e to the power beta E by Z. Then we have P2, which is equal to e to the power minus beta into 0 divided by Z, that's equal to 1 by Z. And we also have P3 is equal to e to the power minus beta into the energy E divided by Z, that's equal to e to the power minus beta E by Z. So we have done with the three states of probability. Now we need the average energy. The average energy, or the expectation value of the energy E, is equal to sum over S, ES, PS. So let's start. First state energy is minus E into PS. PS means corresponding to the first state. So P1 is e to the power minus plus beta E by Z plus uh, the energy of the second state is 0 into e to the power minus beta into 0 by Z. So let's write down here. Plus one more term we have uh, e into e to the power minus beta. What is the third state? That is e to the power minus beta e by Z. So the second term here is going to 0. So what is remaining is minus e to the power beta e plus e to the power minus beta e by denominator is same, so that is Z. Z, if you want, you can replace it with this equation, e to the power beta e. Okay. Now we have a similar question. Find Z, the partition function, Ps, the probability of the finding particle in each state, and the average energy E. And this is a degenerate state. That means there are three energy levels, 1, 2 and 3. The first state is having degeneracy of 2, 3, second state with 2 and third state with 4. And the energy level, the first one has E naught, 4 times E naught and 9 times E naught. These are the energies of the three levels. So let's start with the partition function. Let's write here Z. Z is equal to sum over S e to the power no, this is for degenerate state, so you have to add GS e to the power minus beta ES. GS represent the degeneracy of the each state. So the first state, GS is 3 e to the power minus beta into E naught plus 2 times e to the power minus beta into 4 times E naught plus 4 times e to the power minus beta into 9 times E naught. So that is the partition function Z. Now corresponding to the each energy level, we have the probability P1, that's equal to let us write down in general the PS, that is equal to GS e to the power minus beta ES divided by Z. So P1 will be equal to first state is 3 e to the power minus beta, the energy level has E naught divided by Z, and P2 will be equal to 2 times e to the power minus beta times 4 E naught by Z. Similarly, we have P3, which is equal to 4 times e to the power minus beta into 9 E naught divided by Z. Now this accounts for the three states probability. Now we have the average energy E, which is given by sum over S, GS, ES, PS. So this we will not write GS here because GS will be included in the PS, because PS is equal to GS e to the power minus beta. Okay, so that's equal to ES represent the first state energy, that is E naught. PS is so let us P1. So P1 is 3 times e to the power minus beta times E naught divided by Z plus now we have 4 times E naught. Now PS, that is P2 into 2 times e to the power minus beta times 4 E naught by Z. Last term is 9 times E naught into 4 times e to the power minus beta times 9 E naught by Z. So Z is equal to 3 e to the power, so we can replace this Z by this equation. For the canonical ensemble, we have the partition function as Z given by sum over S e to the power minus beta Es. Now this is tells you about the sum of all possible sum over, or this is sum over all possible microstates. Now this also indicates the total energy, total free energy of the system. Okay, so these are 2 points to remember here. One is the partition function Z is sum over all possible microstates, and this summation is based on, or the partition function is based on the energy Es, so it tells you about the total free energy of the system. Now coming to the thermodynamic potential, associated with the system, we have the total energy, or let us write the average energy U is equal to expectation of E, that's equal to the sum of the kinetic energy plus the potential energy. So this is the average energy of the system, which is sum of the kinetic energy and the potential energy over here. Now F, this is the Helmholtz free energy, HEL, this is HELM, HOLTZ, Holtz free energy. Now this free energy is in with respect to constant volume. The definition is free energy available at constant volume. And we have the G, which is the Gibbs free energy. Gibbs free energy, and this is the free energy at constant pressure. Again we have the H, which is the enthalpy. This tells you about the total heat energy. Total heat energy. So for different thermodynamic potentials, now we can write the Z, which is equal to sum over S e to the power minus beta Es can be written as e to the power minus beta F So Z is equal to e to the power minus beta f, and from this we can calculate f as equal to minus kb t log z. So this is the relation connecting the partition function z and the f, Helmholtz free energy. So this you can derive this from here. From thermodynamical point of view, thermodynamics, we know that the Helmholtz free energy. So we have free energy F is equal to U minus Ts, where U is the energy, here is average energy, and T is the temperature in Kelvin scale, and S is the entropy. So we already know that the F from statistics, F is equal to minus kbt log z. Now from thermodynamic point of view, we can write F as U minus Ts, and differentiating this F is equal to U minus Ts, you can write dF is equal to du minus tds minus s dt, the partial differentiation. Now TDS, now we need to write what is TDS from first law of thermodynamics. We can write TDS is equal to du plus PDV plus it's a minus mu dN, where du represent the energy, u change in energy, p the pressure, v the volume, mu the chemical potential, and n the number of particles. Okay, now just substituting TDS over here, what we get is du instead of minus TDS, we can write minus du minus PDV plus mu dN minus s dt. Okay, so here we have so now we can again simplify this. Du gets cancelled, so dF is equal to minus s dt minus PDV plus mu dN. Now so this is equation 1. So now let us do dou f by dou t. Dou f by dou t is partial derivative of this f with respect to t. So these two quantities will go off, so only minus s will remain. So we can write minus dou f by dou t equal to entropy. So that's the first one. Now with respect to dV, we can write dou f by dou v, dou f by dou v equal to minus p, or you can write minus dou f by dou v equal to p, which is pressure, and the last one dou f by dou n equal to mu. So that is the chemical potential. So three equations here. 1 minus dou F by dou T equal to the entropy S minus dou F by dou V gives you the total pressure, and the chemical potential mu dou F by dou En. And here we have we can also write about another form of the average energy, another form of average energy. So U is given by minus dou by dou beta of log z. It is in terms of partition function z, that is partial derivative of log z with respect to beta. So in conclusion, let us discuss once again all the formula that we have learned in case of canonical ensembles. Canonical ensemble where delta E, that is change in energy, is not equal to 0 and delta N equal to 0. That means there is no change in the number of particles. Now the partition function z is equal to sum over s e to the power minus beta es. The probability ps is equal to e to the power minus beta es divided by z, and the average energy u is equal to sum over s es times ps. Then again we have another formula for u, that is minus dou by dou beta log z. Now F, the Helmholtz free energy, which is at constant volume, is given by minus kBT log z. Apart from that, we have also done about the entropy, which is S is equal to minus dou F by dou T, and the pressure P is equal to minus dou F by dou V, and we have the chemical potential mu is equal to dou F by dou N, and we also have the specific capacity at constant volume. That's given by Cv is equal to dou U by dou T. Now it's a small note kind. We know that beta is equal to 1 by kBT. Now let us do this. Dou beta by dou T is equal to minus 1 by kBT squared. Okay, now we need to write or bring this in this form, that is dou by dou T is equal to minus 1 by kBT squared. Since we have dou by dou T here, we can write here dou by dou beta, bringing this beta to the other. So we can write dou by dou T is nothing but minus 1 by kBT square dou by dou beta. So we have the formula that is written as the entropy. For finding the entropy, we have entropy S is equal to minus dou F by dou T. Now instead of dou by dou T, we can also write this, that is S is equal to minus, instead of dou by dou T, we have minus 1 by kBt squared into dou by dou beta, okay, of the F. So that gives us S is equal to 1 by kBt square dou by dou beta of F. This is another formula for finding the entropy. If F is given in terms of beta, we can use this formula. If it is F is in terms of temperature, we can use the first formula. Now similarly, we also have the CV, which is specific heat capacity, specific heat capacity, CV. So CV is given by dou U by dou T. So here also, instead of dou by dou T, we can use minus 1 by kBt square dou by dou beta of U. Okay, so this is CV. So these are two formulas that we need to remember apart from the regular formula that we know. Just in case U is given in, expressed in terms of beta, we can use this, or if it is in temperature, we can use the first formula. This is a question. Consider a system with energy levels 0 and E. Find the partition function Z, the energy E, Helmholtz free energy F, the entropy S, and CV. Specific heat capacity at constant volume. Now the Z is equal to sum over S e to the power minus beta Es. So there are two levels, 0 and E. So 0 corresponds to 1 plus e to the power minus beta E. So e to the power minus beta, first energy is 0. So first is e to the power 0, which is equal to 1. So Z equal to 1 plus e to the power minus beta E. And the first one, that is U, since Z is given in terms of beta, we can write U is equal to minus dou by dou beta of log Z. So minus dou by dou beta of 1 plus e to the power minus beta E. So the first one, it's log of 1 plus e to the power minus beta E. So log x derivative 1 by x. So we have minus 1 by 1 plus e to the power minus beta E into the derivative of the denominator, that is e to the power minus beta E into minus beta, derivative of minus E, its derivative. Okay, its derivative. Now that's it. So that gives us minus and minus, that is plus e to the power minus beta E divided by 1 plus e to the power minus beta E. So that's the average energy or the energy U. Now we need F, which is the Helmholtz free energy. F formula is minus kBT log Z. So that's equal to minus kBT log of Z value is 1 plus e to the power minus beta e. So that's about the Helmholtz energy. Now S is equal to minus dou F by dou T, but with this we may not be able to go forward. So now what we can do is let start with dou by dou T of F. What is F? Minus kBT log Z. So minus kBT log Z. Now that's equal to dou by dou T of kBT log Z. Now let us consider this as two terms. The first one a u and this is another v. So it is uv differentiation. So this into derivative of this. So kBT into dou by dou T of log Z plus dou by dou T of kBT into log Z. Okay, that gives us kBT times dou by dou T of log Z, dou by dou T of log Z. What is log Z? Log of Z, we have 1 plus e to the power minus beta e plus log Z into dou by dou T of kBT is nothing but kB into kB. Now let's do here. So kB times the second term is kB times log Z plus here we have the term kBT times dou by dou T. This dou by dou T we already know how to replace it with minus 1 by kBT square. So kBT, that dou by dou T we are writing it as minus 1 by kBT square dou by dou beta of log of 1 plus e to the power minus beta e. So this gives us the terms. So second term, this becomes this product. So kb and kb gets cancelled, t and t goes. So minus 1 by t into dou by dou beta of log. So that becomes 1 by whatever is here, 1 plus e to the power minus beta e into derivative of this is e to the power minus beta e into with respect to again beta, that gives us minus e. So finally we have kb log z plus kb log z plus minus 1 by t and also minus of minus it becomes plus and this e is here, so e by t, e by t into e to the power minus beta e divided by 1 plus e to the power minus beta e. So this is the uh, yes entropy here. Now we need Cv, that's equal to dou u by dou t, and we already have seen what is u. U is equal to minus dou by dou beta of log z, that we have got e to the power minus beta e divided by 1 plus e to the power minus beta e. So Cv is equal to dou by dou t of e to the power minus beta e divided by 1 plus e to the power minus beta e. Now we have to convert this dou by dou t. So dou by dou t is equal to minus 1 by kbt square into minus 1 by kbt square into dou by dou beta. Okay, so converting that, minus 1 by kbt square into dou by dou beta of, here we have the terms e to the power minus beta e divided by 1 plus e to the power minus beta e. Here we have the differentiation one. This e can be taken out of this, so minus e by kbt square dou by dou beta of, you can divide and multiply, divide e to the power minus beta e on both sides. I mean, for the numerator and denominator, what you get is 1 divided by e to the power plus beta e plus 1. So this differentiation gives us minus e by kbt squared into dou by dou beta means minus 1 divided by denominator square. What is denominator? That is 1 plus e to the power plus beta e squared into the differentiation of this, that is e to the power beta e into differentiation of beta e with respect to beta, that is e. So we have here minus and minus plus, so e square by kbt square e to the power beta e by 1 plus e to the power beta e squared. Now what happened here is we divided the numerator and denominator by e to the power minus beta e, or let's I mean multiplied by e to the power plus beta e, multiplied by here only in the last term, multiplied by e to the power plus beta e. Okay, so we get this. Dividing by e to the power minus beta e is also same. There is no difference.